So we're going to pick up in lecture set number 2 today. Last class, we started lecture set number 2. So as a reminder, lecture set number 1 was a review of regression analysis. So we have now sort of done a verbal / written overview of how you could go about analyzing a standard regression model. In lab yesterday, we looked at those ideas in some detail. So we basically said, like, here are the 4 steps of the model fitting process, and here's how you could go about doing it in R. And that's effectively the focus of the first assignment as well. And all of that is meant to be reviewed from Stat 378. Lecture set 2, we actually started to look at material that I would imagine that you haven't seen before, or if you have seen, it wouldn't have been in a lot of detail. So the purpose of lecture set 2 is to set the foundation for constructing a generalized linear model. Or more specifically, what we're doing is setting the foundation for understanding how we can formulate a generalized linear model. So there's a framework to fitting these kind of models. There are certain requirements that we place on the response variable. And in order to, one of those requirements is that the response variable belongs to the exponential family of distributions. And in particular, that the response variable can be written in canonical form, where, as we showed earlier, essentially just means that the function a of y is equal to y. So that's what represents canonical form, and this is a requirement of our GLMs. So we have introduced the exponential family. We've looked at 2 different ways that you can write the density of a random variable that belongs to the exponential family. And the 2 examples that we left off with were showing how standard well-known distributions, in particular the normal and the Poisson, they can be their densities can be rewritten in terms of the exponential family notation, and then what each of those components are. So we're going to look at one more example of this to start today's lecture. So just as a reminder of what it means for a random variable to belong to the exponential family. Then we're going to derive properties of the exponential family. So in particular, we're going to find essentially expressions that we can use to compute the mean and the variance of random variables that belong to this family. So general expressions that can be applied across any random variable from the exponential family. Then we will study properties of the likelihood function. We are going to need these later on when we start talking about model fitting, which is the subject of lecture set 3. Under the assumption that we get to lecture set 3 today, we will, as I had sort of just hinted at, we will see some of these properties being reapplied in different settings. Not sure how far we're going to get into lecture set 3. I'd be very surprised if we finished it, but we'll just kind of see how it goes. So again, what we're doing here is laying the foundation for developing a framework by which we can say this random variable would be suitable to fit into a GLM, could be modeled using a generalized linear model. And then we're going to derive properties that we can use in the model fitting process. All right, so as I had mentioned before, the first example is just a reminder of what it means for a random variable to belong to the exponential family, and how we can break that down into its different components. So we want to show that a binomial random variable with density given in equation 8 belongs to the exponential family of distributions. So what we can do here is show that f of y given theta. So theta is the single parameter that we're interested in studying, and little n would be considered the nuisance parameter in this case. So f of y given theta can be written as the exponential of y log theta minus y log 1 minus theta plus n log 1 minus theta plus log n choose y. All right. Okay, so from this, we can see that this again is going to be written in canonical form. So we have a of y is equal to y. We have b theta is equal to log theta, right? Log theta minus log 1 minus theta. So sorry, we can collect like terms with the first two. So a of y is equal to y, and then we're collecting like terms to show b of theta is log theta 1 minus log 1 minus theta. And this is equal to log theta divided by 1 minus theta, which is the log odds. And we'll come back to talk more about what that means later on when we study the binomial GLM in some detail. One of the nice things about this expression is that we can actually measure or explain how the log odds of an event are going to change as one of the explanatory variables changes in the data sets that we're studying. All right, and then we can write that C of theta will soak up the remaining terms. So that would be the n log 1 minus theta, and then d of y not missing anything, right? No. And then d of y will be log n choose theta. Or sorry, n choose y. All right. Any questions? So we've now seen 3 examples of how we can write common distributions in the context of an exponential, in the context of the exponential family, and then how we would break down the components of that expression to show ay, b theta, c theta, and dy. And again, when a of y is equal to y, that means that the distribution is in canonical form, and this is a requirement for fitting into the GLM framework. Okay, so now what we're going to do are derive general properties of the exponential family. In particular, we're going to focus on the mean and the variance because those are the most common expressions or statistics that we would be interested in. And then what we will do is look at the likelihood statistic, or we'll look at properties via likelihood estimation for the exponential family. This will also be important to us, as we will see later on, because this is going to allow us to essentially construct confidence intervals for the model parameters that we are going to study. Okay, so without further ado, let's dig into this here. All right, so we're going to start off. So recall that the integral across y of some density function is equal to 1. Okay, so if we integrate across the domain of any density function with respect to the random variable, that integral is going to be equal to 1. So the area underneath any density curve is equal to 1. All right. So it follows that d by d theta, sorry, I'm going to try and write this as cleanly as I can. D by d theta of the expression given above with respect to y. Sorry, I missed that here. Bad form, Brian, bad form. Is equal to d by d theta of 1, which is equal to 0. And sorry, I'm just going to move this up here just to make sure I have enough room. Okay. So if we integrate any density function, that's equal to 1. If we take the derivative of that integral with respect to the model parameter, that's equal to 0. Right? So therefore, the integral, so d by d theta, that's right. So therefore, if we reverse order of operations, then the integral over y of d by d theta f of y given theta dy is equal to 0. And the integral of d squared d theta squared f of y given theta dy is equal to 0. All right. Okay, so far we have area under the density curve is 1. It follows that the derivative of this expression is 0. And now we're saying if we reverse the order of operations, so we integrate the derivative, this would also be equal to 0. And therefore, the integral of the second derivative would also be equal to 0. All right. So for f of y given theta equals exp a y b theta plus c theta plus dy, we can write d by d theta of f of y given theta is equal to a y b prime theta plus c prime theta times f of y given theta. right. And this expression here results basically just from the derivative of e to the negative ax, right? So the derivative of e to the negative ax with respect to x would be negative a e to the negative ax, right? So this would just be the standard rule for the derivative of an exponential function. So that's why we end up with the f of y on the outside. Okay, any questions so far? Maybe just I'll make a note. All right. Okay, so then following from what we've shown above, right, we can say that the integral, okay, so for f of y, the derivative is equal to this, and the integral, excuse me, over y of this expression here is equal to 0. Okay. All right, so now what we can show is therefore, right, so if we bring the density function inside the expression, so we have the integral of a y b prime theta plus c prime theta times f of y given theta dy. So if we bring f of y inside of this expression, you now have well, I'll just show you. So therefore, the integral of y of a y prime b prime theta f of y given theta dy plus the integral of c prime theta f y given theta dy is equal to 0. Okay, and you can see here that what we have is ay multiplied by its density with respect integrated over y. And that's the definition of the expected value, right? So recall that the integral over y of y times f of y given theta dy is equal to the expected value of y. Actually, maybe I'll try and be as proper as possible. Right? So we have b prime theta multiplied by the expected value of ay plus c prime theta is equal to 0. So the expected value of ay is equal to negative c prime theta over b prime theta. right? And that's our first result. Maybe I'll just move this up too. I was debating whether or not I should use 2 or 3 slides for this. And I was like, no, 2 slides would be enough. And I think I might have made a mistake. I'll just move that up there. And I can okay. Any questions? Does that make sense? Sorry, I'll pull that down too. Okay, so that's a general expression for the mean of a of y from the exponential family. If the if the response variable that we are working with is in canonical form, then we now have an expression for the expected value of y via the terms of the exponential family. So we can do things like, in the case of the normal distribution, confirm that the mean is equal to mu. In the case of the Poisson distribution, confirm that the mean is equal to lambda, which is equal to the variance, like this sort of thing. So it just gives us an alternative representation of some properties that we already know to be true. All right, so the next thing that we're going to do is derive an expression for the variance based off of the exponential family. It's going to be a very similar process, and it's going to use most of the results that we have written above in terms of the integral of the function, in terms of the integrals of the derivatives of the function. Okay, so we're going to start off by saying, I'll just make a little marker here. So to find the variance of AY, okay, we have d squared by d theta squared of f y given theta is equal to a of y b double prime theta plus c double prime theta f of y given theta plus a y b double prime theta plus c prime theta squared f of y given theta. It's a single prime. Right. And that derivative would follow from the product rule. Yeah. Because we're basically taking the derivative of ay b prime theta plus c prime theta fy, and we're going to use the derivative rule to do that, or the product rule to do that. Okay, so this is going to be all right. So we can show since a of y, b prime, or rather, since a of y, b prime theta plus c prime theta squared f of y given theta is equal to b prime theta squared times a of y minus the expected value a of y squared times f of y given theta. Okay, then the integral over y of d squared d theta squared fy given theta dy is equal to b double prime theta times the expected value of a y plus c double prime theta plus b prime theta squared times the variance of a y. Right? And we know that the integral of the second derivative is also equal to 0. Therefore, this expression is equal to 0. So rearranging, so the variance of a of y is equal to b double prime theta multiplied by c prime theta minus c double prime theta times b prime theta divided by b prime theta cubed. All right, and this will be our second result. All right. Now that only took 20 minutes. Make sure I didn't mess anything up too terribly there. right, any questions? Okay, not seeing any. Okay, so those are obviously two major derivations for the exponential family distribution. So we now have expressions for the mean of A of y and the variance of A of y. If the if the random variable of interest can be written in canonical form, that means that we also have expressions for the variance of y and the expected value of y. All right. So the next thing that we're going to look at are properties of the likelihood function. And again, one of the reasons that we're interested in this is because maximum likelihood estimation is the key process by which we actually fit the generalized linear models. So since the generalized linear model framework requires that the response variable belongs to the exponential family and that response variable is in canonical form, it makes sense that we would also require, or it makes sense that we would derive some of the properties of the likelihood function for our exponential or for our random variables from the exponential family, because we'll be able to use those properties later when we're actually working with our GLMs, or with the GLMs that we're going to study. Okay, so we know that the density of y from the exponential family can be written in the form shown here. We've seen this on multiple occasions now. From this expression, we can easily derive a statement for the likelihood function and for the log likelihood function. Okay. So we can show that in this situation. There's a couple of ways that we can do it. We can do it for the single random variable, or we can do it for, okay, we'll start with for the single random variable to get the general expressions, and then we'll see how this will evolve later when we have n random variables in the data set. Okay, so for little n is equal to 1, we are going to have the likelihood of theta given y is equal to the product over I equals 1 to 1 of f of y given theta, which is simply the original expression. Right. So this is our likelihood function. Then the log likelihood function is equal to the log of the likelihood function, which in our case is just going to be A of y, B theta plus C theta plus dy. Right. So in the simplest situation, we have an expression for the likelihood function and the log likelihood function. If we have n observations in the data set, it doesn't overly change this expression. It just means that we're going to have summation sitting out front of ay and dy, and we would have a constant sitting out in front of c theta. Okay. So we could say, note for a sample of size little n, L theta given y will be equal to the sum from I equals 1 to n, ay b theta plus n c theta plus the sum I equals 1 to n dyi. Right. Okay. All right, so in order to maximize a likelihood function, when you're working with the likelihood function for a particular random variable, typically one of the objectives is to find the maximum likelihood estimates. So we want to find the value of theta that makes the likelihood as big, the log likelihood and the likelihood as big as possible. To do this, we're going to derive what are called the score function. We're going to derive what is called the score function, and we'll also show the formation of the information function. The information function is essentially the variance of the score function, so we can use this to conduct inference later on. Okay, so the score function is actually very easy to derive. It's simply the derivative of the log likelihood with respect to the model parameter. All right, so we're going to let S of theta represent the score function. I'm trying so hard to write neat, but I can tell my hand is getting tired, and my brain, I'm saying the word and then my hand is just kind of like scribbling it out. It's a very strange feeling. Okay, so S of theta is going to be the score function. And then we're going to have S of theta is by definition d by d theta of L theta given y. So this is going to be equal to A y b prime theta plus c prime theta. Okay. And then effectively what we do to maximize the likelihood is we set the score function equal to 0 and we solve for theta. And we're going to see some examples of this later on. Okay. Let I of theta represent the information function. Right. I of theta is equal to the variance of S theta. Right. So this is going to be equal to the expected value of S theta squared minus the expected value of S theta all squared. Okay. Hint, the expected value of S theta is equal to 0. Right? This is going to be something I'm going to ask you to prove on the second assignment. So I'm going to give it as a hint now. So if you want, you can start working on this right away. It's like a 2-line proof. And you can show that this is true very easily using the expression given above. Okay, so Therefore, the information function is equal to the expected value of s theta squared. Oh, actually, we didn't even need this. But we can probably end up with the same conclusion. So we'd have to expand the quadratic, carry the expected value through. I've made it more complicated than we need it to be. Okay, I'm going to change this part here. So we don't actually need to do it this way. And I'm going to say note which is equal to this. However, we can easily solve variance s theta squared as follows. So we have I theta is equal to variance s theta, which is equal to the variance of a y b prime theta plus c prime theta, which is equal to b prime theta squared multiplied by the variance of a y. All right, and then from above, from our previous expression, we know the variance of a of y from the last slide, or from 2 slides back, is b double prime theta times c prime theta minus c double prime theta b prime theta over b prime theta cubed. So if we sub in our expression for variance of ay here, we will end up with, so this is equal to b double prime theta c prime theta divided by b prime theta minus c double prime theta. And those are the 2 main results from this. Okay. Any questions? Cool. Okay, so I've mentioned a few times that basically a generalized linear model requires that the response variable that you are studying belongs to the exponential family and can be written in canonical form. Okay, so formally, GLMs were introduced in 1972 by Nelder and Wedderburn. There's a very long book written by it might be written by Netter, Wedderburn, and Nelder, but I think Nelder's a part of it for sure. That came out in 1989. It's sort of like the Bible of generalized linear models. So GLMs are defined for a set of independent random variables. So we still have the independence assumption that we would have had on the regular linear model as well. And this makes sense because, again, the standard linear model is a special case of a GLM. So an assumption like independence is not all of a sudden going to not come into play. So for a set of response variables y, we assume that each response variable belongs to an exponential family, can be written in canonical form, and they depend on a single parameter theta I. So we can re-express our notation for the exponential family of distributions. Sorry, what I mean is we can re-express the density for the exponential family of distributions in terms of each yi for I equals 1 to n. Now, obviously, when we're formulating the GLM, we're going to assume that the yi are the same across all n observations. Otherwise, like, what are we trying to fit, right? Like a binomial normal or something across the model. So we're going to assume the same distribution for all of the response variables. And that's common practice, even in the regular linear model case. Okay, so then we can say that the joint probability density function of y1 to yn is given in by the following expression. And this would be the same thing as the likelihood. Okay, so when we fit the GLMs, our actual goal is to link the mean of the response variable to a set of regressors. So we're not explicitly interested in studying the theta I, but we're interested in studying the model coefficients beta 0 through beta k. Right? So we're going to say that we have the expected value of the response variable is equal to mu I, right? Where mu I is a function of the theta I. And then we are going to transform the mu I using that link function we talked about before, such that g of mu I is equal to xi transpose beta. And this is the general form of our generalized linear model. In this situation, g is a monotone differentiable function. And we've defined this earlier on in the lecture set. We call it the link function. Now, what I mean when I say it's monotone is that it is a function of mu that either increases or decreases in one direction. So it can't do both. It's strictly increasing or strictly decreasing. As previously defined, the xi are basically just the explanatory variables that exist in the data set, and the beta is the vector of model parameters. Okay, so what we're going to look at now are a few examples of how we can formulate a GLM in different situations. All right. So the first example, and sorry, just before we get to that first example, it's just a little summary of those 3 points. So we're looking for 3 components: a response variable that belongs to the exponential family, a set of model parameters, our explanatory variables, and then a definition of a link function. Okay, so we'll start off with the most familiar case, which is the normal linear model situation. So when we first study linear regression, and in particular, we study multiple linear regression, though we could use a similar expression in the SLR case, I suppose. Yeah, you could use a similar expression in the SLR case. We have y is equal to x beta plus epsilon, right? Where x beta represents the signal and epsilon represents the noise. In terms of the GLM framework, we would have the following. So we have 3 components to specify. The first component is going to be that the yi are normally distributed with mean mu I and variance sigma squared. Okay. So, and we know that the yi in this situation would be a member of the exponential family because we've already shown that this is true earlier on. Now we're just doing it across for I equals 1 to n, but it would be the same result. In part 2, we simply have the definition of the xi and the beta. So here we're going to have x is x11 through x1k, xnk, x1n. And the beta will be the vector of model parameters, beta 1 through beta k. And then we can also include an intercept term in this if we were interested. So we could put beta 0, and then we just need a leading column of 1s in the design matrix X. But for illustrative purposes, it doesn't matter. Okay, and then the last thing we need is the link function. So we're going to say g, which is the link function, is the identity function. And in this case, we have g of mu I is equal to mu I, which is equal to x I transpose beta. Any questions? Cool. All right, so that would be the most familiar example. Normal model is a special case of a GLM. Okay, second illustration. So now we're going to look at a situation where we can model something as a binomial, or in this case as a Bernoulli, but that's a special case of a binomial. Okay, so first off, just to set up the explanation, we're going to define a cognate, or rather a cognate is defined as a word that is related in origin to another word. So this would come into play, for example, if you have one language that's a descendant of another language, and then there's going to be similar words that are related across those two languages. Okay. So let's suppose that we can model the probability that the two related languages have cognate words using the expression in equation 11, where theta is some parameter to be estimated and t is the amount of time that separates the two languages. So this is a fairly easy problem to set up. We can say that y1 to yn are going to be binary variables where they're equal to 1 if the languages have cognate words for the meaning of word I, and it's equal to 0 if the words are not cognate. Okay. So we can say that the probability that yi is equal to 1 is equal to e to the negative theta t, which is equal to pi. Okay, so the probability of the words being related. And the probability of yi equal to 0 is equal to 1 minus e to the negative theta t, which is equal to 1 minus pi. So the probability of the words are not related. That word I is not related specifically. Okay. Okay, so this is a Bernoulli distribution, which is a special case of the binomial. So in terms of the GLM framework, we can write 1, yi is distributed binomial n comma theta, where n is equal to 1 and theta is equal to pi. Okay, so we've shown before, kind of like I talked about, oh yeah, and this would be for I equals 1 to n. Okay, so we've already shown that the binomial distribution belongs to the exponential family of distributions, and it can be written in canonical form. Okay, in part 2, we need to specify x and beta. So here we would have xi is equal to negative t, and beta is equal to theta. Right. And then in part 3, we would basically say G is going to be the log function, for example. So we could write G of mu I is equal to G of the expected value of yi, which is equal to G of pi, which is going to be log pi. Therefore, log pi is equal to negative theta t. All right. You can use regression for anything. Okay. We will get more clarity, I think, into these types of examples once we actually start to study the binomial GLMs. Again, the purpose of these illustrations is just to go over the 3 steps of the GLM framework. So step 1, response variable in terms of the exponential family. Step 2, definition of xi and beta. Though in a lot of the cases that we're going to look at, the definition of xi and beta is going to be very straightforward. It's going to be much more similar to the sort of traditional setup, in that, you know, X is going to be the design matrix and beta is just going to be your set of model parameters. And what we'll see once we start studying, for example, binomial GLMs in detail, is the influence of beta will depend on the link function you use when you're modeling the probability of success from that binomial distribution. So those beta values are actually going to represent changes in like the log odds, for example, or the probability of success, this sort of thing. And a lot of it, again, comes back to the structure of the response variable. But we're going to see these in more detail, and we're going to see better examples of these once we get to that point. Again, these examples are just to try and illustrate how we would fit something into that into the framework. Though theoretically, we should be able to fit this model as well. Maybe I'll try and come back to find an example that works well in this case. Okay, so we'll look at one more illustration using the Poisson distribution. So in this illustration, we're going to say let y count the number of deaths from a non-infectious disease. So basically, like just number of deaths occurring naturally in some population. We know that the density for a Poisson distribution can be written as f of y given a rate parameter. In this case, I've called the rate mu. You can also call the rate lambda. Actually, I think I should have called it lambda here. But anyways, so we have f of y given mu is equal to mu to the y e to the negative mu over y factorial, right? So this is just the general definition of a Poisson random variable. Y is a whole number count. Typically, we use the Poisson when we have sort of like a rare number of occurrences that exist as whole numbers. And then mu is equal to e of y, obviously by definition, which is also equal to the variance. Okay, so we can say that if we're interested in modeling number of deaths, the expected value of y is going to be equal to n times lambda times x transpose beta, where n is the population size, and this lambda x transpose beta is the rate of the occurrence per 100,000 people per year. All right, so let's consider some data coming from New South Wales in Australia in 1991. So we have counts of the number of people that died in certain age groups between 30 and 69. So you can see here that we have age groups separated by 5-year categories. So 30, 31, 32, 33, 34, from 30 to 69 years old. And in the second column, we have the death rates, which were computed using the total counts and the population size. And then we standardize by multiplying by 100,000. Okay. In the plot to the right of our table, we have the log of the death rate as a function of age group. Now, this actually does look a little curved to me, but we're going to assume, just for the purpose of illustration, that this could be fairly well approximated using a straight line relationship. So even though there is kind of a curvature here and it's probably a bit of a stretch, just for the purpose of setting up the model in this framework, we're going to assume that we can fit a straight line to this. Okay, so we're going to propose that we can model mu using the function ni e to the theta I, where I just represents the age group that you are within. So in this situation, we're going to have yi is distributed Poisson with parameter mu I, with rate mu I, for I equals 1 to n. And then in part 2, we are going to say, we're going to let xi equal log and I, and we're going to let the beta equal 1 theta. Okay. So then in part 3, we would say G is going to be, again, the log function such that G of mu I is equal to the log of mu I is equal to log ni plus theta I. All right. Okay, do you guys have any questions? And or concerns and or comments? All right. Okay, so in this lecture set, we introduced the framework for formulating a generalized linear model, and we introduced the exponential family distributions. We looked at examples focusing on the normal distribution, the binomial distribution, and the Poisson distribution. A little bit of foreshadowing there because those are going to be the three main the binomial and the Poisson are two distributions that we're going to study in detail. We're not going to focus too much on the normal because that's just the standard linear model, but there will be some questions that refer to that particular model on the assignments. What we're going to talk about in the next lecture set is model fitting. So lecture set number 3 is devoted to the estimation of the parameters for a generalized linear model. So we're going to learn how a generalized linear model is actually fitted. This is done through an iterative procedure. So we're going to talk about maximum likelihood estimation, and then we're going to talk about a common approach for estimating MLEs when you can't find closed form solutions. That's called the Newton-Raphson. And then we're going to show how the Newton-Raphson is essentially adapted for generalized linear models. And what we end up with is a procedure called the iterative weighted least squares approach. And the IWLS is the procedure that sort of underlies the process of fitting GLMs. And actually we can show through practice that this procedure, which we'll define and we'll look at an example of at the end of the lecture set, you can prove that in R, it's the same process that's being utilized. Kind of like least squares regression or standard maximum likelihood estimation for the linear model. Okay, so for generalized linear models, the maximum likelihood estimation is the procedure that we typically employ. Unfortunately, for the majority of the GLMs that we are going to study, you can't derive closed form expressions for the parameter estimates. So you can't find, in the way, so for the SLR model, for example, the simple linear regression model, we could show that B0 is equal to Y bar minus B1 X bar, and B1 is equal to SXY over SXX, right? So we can't directly show that is, we can't find expressions that are neat and clean like that in the case for most GLMs. So what we have to do is use iterative processes, which basically means that we find an expression for the MLE, which is not going to be closed form. And then what we do is we basically use that expression to sort of move ourselves as close as possible to the area where we maximize the likelihood. And we do it in a sequential process. So we start at some point, and then we update that point to get a new value, and then we update that point to get a new value, etc. One of the processes that is, or an iterative process for finding MLEs that is pretty well known and pretty popular and pretty easy to implement is the Newton-Raphson algorithm. Okay. It's not the only type, there are others, but it's one type. Okay, so very briefly, the Newton-Raphson algorithm is a root finder. So basically, given some real valued function that has a, that is maximized at a single point, the Newton-Raphson is an approach that will essentially move you to that point. Okay, so it'll find the value of an expression when you set it equal to 0, such that that value maximizes said expression, right? So the score function or the derivative of some real valued function set equal to 0 would be an example of what you would be utilizing to try and maximize that function. Now, in the context of maximum likelihood estimation, we can write our Newton-Raphson in the general form as theta hat at iteration k. Okay, so this is going to be the estimate of the MLE at iteration k. Okay. Is equal to the estimate of the MLE at iteration k plus 1, k minus 1, minus the score function evaluated at theta k minus 1 divided by the derivative of the score function evaluated at iteration k minus 1. So you can see what's happening here is you're basically saying start at some point, derive the score function and the derivative of the score function, plug in your starting point, take the difference between that starting point and this ratio to find your next step, your new value, and then take the new value, replug it back in, and keep cycling through until you reach convergence of some type. Okay, and we're going to look at a more detailed example of this momentarily, but that's the idea. So you're just kind of like moving yourself along the curve until you hopefully reach the global maximum. Okay, we can also show that given the expected value of S prime theta is equal to the negative of the information function, this is something else that you're gonna show on assignment 1. Again, it's a pretty simple proof. That the Newton-Raphson algorithm that we showed on the previous slide can also be written as theta, the estimate of the MLE at iteration k-1, plus the score function evaluated iteration k-1 over the information function at theta at k-1. Now, I'm gonna show you examples of both of these in the context of using a distribution that belongs to the exponential family. And both solutions in this example are going to reach the same conclusion. So it's kind of like a check. This approach and this approach both reach the same point. They take a very slightly different path in this particular illustration, but the expectation, I think, would be that you can use either setup and arrive at the same goal. And a lot of the time, the difference is simply just, well, in this case, the advantage is that we have expressions for the score function and for the information function. We found those in lecture set number 2. So we could easily set up our Newton-Raphson given those general expressions. Whereas we don't have exactly an expression for S prime of theta readily available, but it's not overly difficult to derive either. All right, so we're gonna look at, well, we're gonna start an example that illustrates the Newton-Raphson. So we have a sample size of 49, and our sample is measuring time to failure of these Kevlar epoxy vessels. All right, so the data here is measured in hours, and each of these is how long it takes for one of these vessels to fail. Right? So when we're modeling failure time, a common distribution that's utilized is the Weibull distribution. And the density of the Weibull distribution is given on slide 6. So we have f of y given lambda theta. That's a little bit of a setup because we're going to use theta as our single parameter for the exponential. So f of y given lambda theta is equal to lambda times y to the lambda minus 1 e to the negative y over theta to the lambda divided by theta to the lambda. So that's just the PDF for the Weibull. Lambda here is considered a shape parameter and theta is considered a scale. And this distribution only exists for the positive real values. All right. So we can show that this distribution is a member of the exponential family. So we can say f of y given lambda theta. So we're going to say that this is our nuisance parameter here. Okay. Is equal to lambda y lambda minus 1 divided by theta lambda exp negative y over theta lambda. So then we can say, in terms of the exponential family, that this thing is going to be exp. So we would have lambda minus 1 log lambda y log lambda minus plus lambda minus 1 log y minus lambda log theta minus y over theta lambda. So in this situation, we can see that a of y is going to be y to the lambda. B of theta is going to be theta to the lambda, negative. C of theta should be log lambda minus lambda log theta. And dy is going to be equal to lambda minus 1 log y. All right, so this is not in canonical form unless lambda equals 1. Okay, so from this definition, we can conclude that the Weibull distribution would actually not be suitable in a GLM framework unless lambda was equal to 1. Okay. Okay, so the next thing that we need to do to set up the Newton-Raphson is actually derive the score functions. So we have to go through the process of finding the likelihood function, the log likelihood function, then find the scores, and then we would substitute those. Then we'd find the derivative and we'd substitute those in to set up our Newton-Raphson. Not going to be able to do that in 2 minutes. So I think I'll just stop here for today. And then on Tuesday, we can start with a review of what we're looking at. And then we'll set up the Newton-Raphson and look at an example. And then we'll move on to derive the parameter estimation scheme for the GLMs. All right, so I'll stop here. Jan 13. All right, so with that being said, have a good weekend. We don't have anything due this week. Assignment 1 is not due till next Friday. And I will talk to you guys on Tuesday.
Can I ask a quick question?
Yeah, definitely.
Since we have an expression for the expectation of a of y,
yeah,
could we then use that to find the moments of the Weibull distribution? Like just for different values of lambda?
yeah, for sure. You could, because the moments, it's just like
Y to the power. The rth moment is the expectation of y to the power of r.
Y to the power of r. You could definitely find the first. Oh, I understand what you're saying, because lambda, you'd have like y to the 1, y to the 2, y to the
Yeah.
3. Yeah, I think that would work out. You could check it.
Okay. Cool. I was just curious.
No, it's a good question. Let me just see real quick if I can, because Wiki, if Wiki lists the moment, oh yeah, let's see, they have it right here.
Because then, yeah, you could just sub in different values. So it'd be 0 minus log of theta.
Yeah, because you'd have, well, you'd have the expected value of y to the 1. So the expected value of y would be the mean. Then you'd have the expected value y to the 2, but you would still need to solve, like you would still need to work out what the expected value of y to the lambda is, like in a general.
Oh, okay.
You know what I mean?
Yeah.
Like you'd have to take the integral like y squared.
Yeah.
Or it wouldn't really give you a, it wouldn't be a faster way of doing it.
Mm-hmm. Okay, cool. Anyways, thanks.
Yeah, good question.
Okay, see ya.
All right, see ya.